Today we'll be talking about Faraday's law of induction as well as Lenz's law. Now first off, let's consider what is induction. Induction. Well, one thing to recognize is how we came up with a magnetic field. So we created a magnetic field by having a current. A current, which is to say moving charges, and thus a change in the electric field. Now, induction is sort of the opposite idea, which is that when we have a change in our magnetic field, we're going to produce a current. And this current is called induced current. And that brings us to Faraday's law of induction, which states that when we have this change in magnetic field, and in this case we're going to introduce a new idea called the magnetic flux, which when simplified is just B times A, where A is the area, we find that an EMF, or electromotive force, is going to be created. And this is equal to negative the derivative of the magnetic flux over time. And this negative sign we call to be Lenz's law. Now, what does this idea mean? Well, it's the idea behind induction, which is to say, let's say we have a magnetic field, a uniform magnetic field like so. And now we have a coil of wire. Now originally there is zero current running through the wire when the wire is at rest. But what happens when we start moving the wire with some velocity towards the right? Well, what we find then is that the magnetic flux is going to change. In this case, the area is just going to equal to the area of the inside the wire loop. However, what we find is that the amount of field lines that are passing through the loop is going to decrease since we're moving away from the magnetic field. So as a result, an EMF is going to be created, which is a change in which is measured in voltage. So as a result, we're going to produce some induced current I. But now we want to know what's the direction of I. And in that case, that's where Lenz's law comes in. Lenz's law states that it wants to oppose the original change in the flux that caused the EMF. Which is to say, we can sort of think of it in terms of magnetic inertia. Where the idea behind inertia in terms of a gravitational field was that when we give an object some force, it wants to resist the movement of that force. And the same kind of idea about inertia goes for our magnet. Which is to say that we created this induced current. However, what we find is that the current is going to resist this change. So initially, while the amount of field lines is decreasing, we're going to try and induce a current that will cause this to once again increase back to the original. So namely, we want to create a current that will induce more field lines that go into the page for the magnetic field. And by using the right-hand rule, we find that in order to do so, we want our current to be counterclockwise. And the same idea holds true if we push our wire the other way. Namely, here we start off with our wire. And once again, while the wire is at rest, there is zero change in magnetic flux. And there is no induced current. However, once we start moving our wire towards the left with some velocity, then what we find is that the amount of field lines of the magnetic field is going to increase. So we want a current that will decrease the number of field lines, which is to say we want to create a current that creates field lines in the opposite direction, namely out of the page. So in order to do so, once again, we use the right-hand rule, and we find that we want our current to be moving clockwise. So thus we have that Faraday's law of induction states that the magnetic field and an electric field or a current is going to be related. And the way they are related is, namely, if we have a change in magnetic flux, which is related to the area and to the changing magnetic field, then we're going to have some current created, called the induced current.